Housed within the Missouri S&T Student Design and Experiential Learning Center, more commonly known as the SDELC, is the Missouri S&T Rocket Design Team.
Hello, my name is Andrew Schleshman. I'm team educator here on Rocket Design Team. I'm a sophomore physics major. I'm going to talk about our Rockets in U program. Rockets in U is a couple week long program that we get new members introduced to rocketry, covering all of our sub teams and subgroups, what a rocket is, how to build one. We cover how to do a level 1, stuff like that. And then somewhere in the middle there, we talk about Argonia Cup, which perfectly leads into our Argonia Cup build season.
Hi, my name is Macy Odom. I'm a sophomore studying aerospace engineering, and I'm one of the team educators on the Rocket Design Team. So something else that we do as team educators is oversee the Level 1 program. We can have members of the Rocket Design Team submit Level 1 designs, and once they have it approved by us, they can come in and start building. Once they have it completely built, we will then take them out to Springfield, Missouri, where they will launch it and become officially Level 1 certified.
Hi, my name is Madeline Stidham. I'm a junior in mechanical engineering and engineering management, and I am this year's chief educator for the Missouri S&T Rocket Design Team. One of the biggest portions of team education and that subgroup is the Argonia Cup rocket, which you can see the people behind me working on. We use this opportunity to teach new members about the designing and manufacturing processes we use on this team and take it into our solid and liquid projects as well. So for this project, me, Macy, and Andrew, basically the leadership that makes up team education, are the only prior people who have experience with Argonia Cup and its requirements. So we act as more of mentors to our freshmen or new members on the team to teach them about these design and manufacturing processes.
My name is Caitlin Stam. I'm a freshman in ceramic engineering. So we had our CODR and our IDR during the fall semester to gain input about our rocket from the rest of the design team. And near the end of the fall semester, we started the building process for our rocket with our fin layups. Starting this spring semester, we started working on the rest of the rocket. The sustainer logic and flight simulations are going to be finished February 20th. The rocket is planned to be finished March 1st, the ejection testing finished by March 8th, and the integration practice finished the week of March 16th.
Hi, my name is Andrew West. I'm a freshman in aerospace and mechanical engineering. Starting with the rules for this competition, the biggest rules that matter to us are the motor combination being no greater than 5,120 Newton seconds. This is also known as the impulse. The motor inhibition logic shall prevent motor ignition if the tilt is greater than 20 degrees from the vertical, flight speed is less than 200 feet per second, and the next rule is thrust to weight off rod is 5-to-1, as well as both stages being recovered in a reflyable condition.
Hi, I'm James Fink, freshman in aerospace and mechanical engineering. We started by taking our design from last year, Pharaoh, into Open Rocket and changing it according to this year's conditions. The biggest factors that went into the design were that the scoring system incentivized minimizing impulse, while also having more space for golf balls. In addition, this year we could buy a transition piece, so we decided that we would benefit from having a 4-inch diameter booster and a 3-inch diameter sustainer. First major change that we made to the old Pharaoh design was converting it so it would integrate the 4-inch to the 3-inch transition piece. After that, we looked at a new motor combination that would result in less impulse this year. We looked for motors with low impulses but long burn times. We shortened everything but the nose cone, which we increased in length so we could store more golf balls than last year. In all, Pharaoh and Basilisk ended up being the same length, but because of the nose cone, we can have more golf balls. However, because of the transition piece, that means less mass and they can therefore go higher.
My name is Galen Willoughby, and I'm a freshman in aerospace engineering. Basilisk is our first transition-style rocket containing a 3 to 4 inch transition piece between the booster and sustainer body tubes. Each piece, including this transition piece, is all COTS components. Both stages of our rocket feature a dual deploy recovery system in which, soon after the separation of the booster's apogee, the booster's drogue will deploy, and the main after that. The sustainer's drogue and main does the same at the sustainer's apogee. Each stage has an electronics bay to optimize altitude and location tracking. For the competition, the score is based off of altitude and payload count, so more points being given to the higher payload and higher altitude. This being in mind, our rocket will have an internal coupler extension attached to the nose cone to hold our payload for a better score.
Hello, I'm Christian Light. I am a freshman in aerospace engineering, and the transition piece used in the rocket is a very important component in the flight of it. The part itself is only about 7 inches tall with a 3 to 4 inch diameter. Despite its small size, it is vital for stage separation in order for the rocket to function properly. It is connected to an 8-inch lower coupler with bolts. This lower coupler is connected to the booster using shear pins. A 5-inch upper coupler connects the transition piece to the sustainer using the same combination of bolts and shear pins. The upper pins also include black powder charges. These charges, in combination with the shear pins, allow the transition piece to disconnect from the rocket whenever the booster burns out and the sustainer needs to fire. The stage separation is caused by an electrical pulse being sent from the upper electronics bay towards the black powder charges. This causes the charges to ignite and explode with just enough force to disconnect the shear pins from the transition piece. This separation allows the sustainer to ignite with little to no issues.
I'm Adam Calabrese. I'm a sophomore in mechanical engineering. Our rocket's payload is designed to be contained within the nose cone of the rocket, which greatly increases our rocket's stability by placing more mass into the nose cone. In our design, we decided on a 15-inch nose cone. However, we were only able to fit a total of 5 golf balls into the nose cone, which was not optimal for our score. To increase the payload capacity of a rocket, we added a nose cone extension consisting of a 13-inch body tube attached to the nose cone and body tube housing the motor and recovery system within the 20-inch tube coupler. This extension coupler allows for an additional payload capacity of 11 golf balls, as well as serving as the housing unit for the sustainer's electronics bay, thus bringing our total payload capacity to 16 golf balls, allowing for a higher score.
Hello, my name is Lana Ryan. I am an aerospace engineer, and I am a junior in said department. This year's scoring prioritization was more on the total impulse and altitude. Specifically, this year the competition is focused on achieving a lower total impulse with as high an altitude as possible with this lower total impulse. The change in the scoring is much different compared to last year's scoring, which prioritized the number of golf balls a rocket could carry. This newer scoring still utilizes the number of golf balls that the rocket can hold, but this isn't nearly as impactful on the score as we wanted. But aside from what was important to the score, I'm here to talk about how the score was achieved and how we found the best balance for payload weight, aka the number of golf balls in the rocket, the total impulse, and the maximum altitude reached by the rocket given its impulse. What we did was we tried a multitude of motor combinations, found their combined impulse, and tracked how their altitude and stability fluctuated with these combinations. In an Excel spreadsheet, we calculated the scores achieved at different numbers of golf balls, seeing how many golf balls we could get into the nose cone before we reached a stability level of 3. With this helpful Excel spreadsheet and the constant comparison of different motor combinations, we found that the ideal score would be achieved by having 16 golf balls in the nose cone with a motor combination that will be discussed momentarily.
I'm Tyler Trost. I'm a freshman in aerospace engineering. For our competition, we found that we want to have max apogee with the least amount of impulse, which will give us the highest amount of points we can get. So for our team's rocket this year, we decided using the K375NW motor in the booster. It has a total impulse of 2,240 Newton seconds and a burn time of 6 seconds. In the sustainer, we will be using a J135W motor in our sustainer with a max impulse of 1,042 Newton seconds and an 8-second burn time, giving us a grand total impulse of 3,282 Newton seconds and a burn time of about 14 seconds. These are the motors we'll be using, but we need to wait for them to ignite. The ignition system will light the motor if the rocket has less than a 20-degree tilt and exceeds 200 feet per second.
For our recovery system, we have a 2-foot drogue on each of our booster and our main. We also have a 4-foot main chute for both our booster and our main section. Each of these parachutes are connected with 1/4-inch Kevlar shock cords to their respective body tubes. Those shock cords are 3 times the length of the sections they're attached to. The drogue chute is meant to deploy at apogee, and the main chutes are meant to deploy when the tube reaches 1,000 feet. The ground head velocity for both sections is under 35 feet per second, which is our safety limit.
I'm Jonathan Christ, a freshman in computer engineering. Our rocket has many electronics that are used for ignition, separation, recovery, and data acquisition. The Argonia competition requires our electronics to be redundant. primarily for safety reasons, meaning we have 2 altimeters per stage. Our booster altimeters only need to control booster recovery, meaning igniting the black charges so our parachutes can deploy, as well as actually deploying the parachutes. To do this, we have carefully selected a primary Altus Metrum Telemega for its GPS capability, so we can track it once it returns to us on the surface. Our secondary altimeter is the Altus Metrum Easy Mini, which will handle parachute deployment if the Telemega malfunctions. Similarly, our sustainer altimeters need to do the same job as in the booster within the addition of stage separation at booster apogee, igniting the sustainer motor and deploying at apogee. To execute these functions, we once again have a Telemega as our primary altimeter and an Altus Metrum Easy Mega as our secondary altimeter. All 4 altimeters will be powered by a LiPo battery and held onto a custom 3D printed electronic sled, both of which are contained in their respective couplers.
So this is our rocket for the 2025-26 Argonia Cup. Its name is Basilisk, and thank you to the new members who put in so much time and energy into this rocket. It looks fantastic. See you at the competition.